Okay, picture this. You're standing outside a massive industrial plant, staring up at those towering pressure vessels, the endless mazes of pipelines, and all that crazy heavy machinery. And you find yourself wondering, how do we actually know that all of this metal can handle the immense crushing stress it's put under every single day? Well, you are in the perfect place. Today, we are decoding the highly technical world of plant material properties and translating it into something completely accessible. In this explainer, we're going to strip away all the complex jargon and look at the actual DNA and the professional resume of the metals used to build our world. It really all starts with this one kind of terrifying question. How can we be absolutely sure giant plant equipment won't just explode? I mean, when you've got toxic or highly volatile chemicals boiling inside a massive steel tank at incredibly high pressures and temperatures, guessing is absolutely not an option, right? The answer here isn't just about drawing up a good design. It relies entirely on verifying the exact chemical and physical properties of the materials you're using. Because if the metal itself isn't up to the task, the whole system fails. So how do engineers actually verify this out in the real world? Okay, let's dive into this. Here is our roadmap for the explainer. 1. Material basics. 2. Chemical properties. 3. Physical properties. 4. The mill certificate. And finally, number 5, verifying with ASME codes. Let's get to it. Starting off with Section 1, Material Basics, specifically iron and alloy. To really understand the physical limits of plant equipment, we first have to look at the fundamental building blocks. Out in the plant industry, materials are broadly divided into non-ferrous and ferrous materials. But the vast majority of what you'll encounter are ferrous materials. By definition, a ferrous metal is primarily composed of iron. But here's the catch. Pure iron on its own, it isn't quite right for hardcore industrial use. So we mix it with very specific alloy elements. Think of it like baking. It's this precise mixing of iron and alloys that creates the distinct, heavy-duty mechanical characteristics needed to survive a high-pressure plant environment. Which brings us right into Section 2. Chemical properties, or what I like to call the material's DNA. Every single piece of metal out there has a completely unique chemical makeup that dictates its ultimate identity and its capabilities. Take a look at the elements listed in this table. You can think of this literally like a nutrition facts label on the back of your food, but instead it's for industrial carbon steel, specifically a material known as SA516. Notice how just tweaking the elements completely changes the grade of the metal? For a grade 55 metal, the absolute maximum carbon allowed is 0.18%. But let's say we need a stronger grade 70 metal. To get that, we allow carbon to bump up to 0.27%, and we increase the manganese from 0.90 to 1.20%. Just these tiny percentage changes in this chemical DNA dictate exactly what this metal is going to be capable of when it's out in the field. Moving right along to Section 3, Physical Properties and our Ultimate Strength Limits. So, that chemical DNA we just talked about, that directly creates our physical properties. If the chemistry is the DNA, the physical properties are the gym limits, meaning exactly how much stress this metal's physical body can endure before it completely fails. To wrap our heads around physical limits, let's actually use a gym analogy. First up, we have yield strength. This is the exact point where a metal starts to permanently deform. In the gym, this is like pulling a muscle, right? You push way too hard, you didn't break a bone, but you've caused permanent damage, and you simply can't snap back to normal. Tensile strength, on the other hand, is the absolute maximum stress a metal can handle before it completely fractures. In our analogy, this is when your muscles completely give out and you drop the heavy barbell right on the floor. Now translate that to a real plant. Surpassing yield strength means your tank is permanently warped and bent, but surpassing tensile strength, that means your tank has literally exploded. Now, there is one more absolutely critical physical property you need to know: elongation. This is the percentage a metal can actually stretch or lengthen before it hits that catastrophic breaking point. Essentially, this measures the metal's flexibility or its ductility. And this is huge because you do not want a metal that is so brittle it just shatters like a glass window under pressure without any warning whatsoever. You want it to stretch out a little bit first. Missing any of these 3 physical limits, yield, tensile, or elongation, in a plant design scenario leads directly to a massive disaster.
All right, Section 4, the mill certificate.
Okay, so we've covered the theory, but how do we actually prove it? Look at this document. When a vendor sells metal to a plant, they are required to provide this piece of paper, called a mill certificate. It is literally the resume of the metal. It proves those specific chemical and physical traits we just covered. Now, what's really interesting about this slide is if you look closely at the columns here,
You can clearly see the yield strength, labeled YS, the tensile strength, labeled TS, and the elongation, labeled EL. The vendor physically tested a sample of this exact batch of metal and recorded exactly how it performed in the lab, proving its gym limits on paper.
Finally, Section 5, verifying with ASME codes. Here's the thing. Engineers don't just blindly trust a vendor's resume. Enter the ultimate rulebook, ASME Section 2, Part A. The American Society of Mechanical Engineers publishes these massively comprehensive codes, and they essentially act as the law in the plant industry. This specific book dictates the exact chemical and physical requirements that every single certified material absolutely must meet. For example, if you want to claim your metal is an SA240 grade 304L stainless steel plate, this book tells you exactly what that means in terms of its core properties. No exceptions. And this brilliantly illustrates exactly what's inside that law book. On the left side, we have the chemical composition limits, the DNA rules, and over on the right, we have the mechanical test requirements, the minimum physical gym limits, like our tensile strength and yield strength. Engineers look up their specific metal in these exact tables to establish the baseline requirement for safety, based entirely on these distinct properties. So let's put this all together into the exact, and honestly very satisfying, 3-step workflow that a mechanical engineer uses every single day to track these critical attributes. Step 1. You receive the mill certificate from the vendor. This is the metal's resume. Step 2. You open the ASME Section 2, Part A. This is the law book. Step 3. You carefully compare the chemical and physical values. You look directly at the vendor's test results, and you cross-reference them to ensure they fall safely within the strict limits set by the ASME code. If the chemical and physical properties match the requirements, boom, the metal is approved for the plant. If they don't, it is rejected immediately. No second chances. Which brings us to a final thought I want to leave you with. To an outsider, cross-referencing a mill certificate with an ASME codebook might just look like boring, tedious paperwork. But ask yourself, is it just paperwork, or is it actually the absolute last line of defense for plant safety? When you fully grasp that these specific chemical percentages and physical limits are the only things keeping high-pressure tanks from turning into literal bombs, you realize that mastering these properties isn't just academic theory. It's the daily practice of saving lives. Thank you so much for joining me today to decode the DNA and the resume of metals. Stay curious, keep learning, and I'll catch you on the next explainer.